In this video, we're going to be looking at more applications of integration, namely work and other applications. So you may be familiar with the formula from physics that says that work is equal to force times distance, and that applies when your force is constant. But what we're going to do is generalize this formula. Imagine that our force now depends on the distance x at which it's acting. And the new formula for work looks like this. Work is going to be the integral from a to b. What we're integrating is our force. So integrating the force with respect to x. So let's put a star beside this. We're going to use this formula in the next 3 examples. And if you want to convince yourself that this is true, you could do units analysis here. So when you're looking at an integral, just look at the integrand including the differential and think about units. So force would be measured in newtons, and this dx, that's a little chunk of distance in the x direction, that would typically be measured in meters. So sure enough, you would get Newton meters, or you could say joules, which is the correct units for work. First example, let's find the work done in winding up 30 meters of a 50-meter chain that weighs 2 newtons per meter. So let's imagine some of our chain is already wound up and some would be hanging down. We're going to let x equal the length of chain that's already wound up. So since this chain is 50 meters long, if you've got x meters already wound up, then you have 50 minus x is the length of the chain that has yet to be wound up. And you could just put a little x here to represent that's how much length of chain has already been wound up. So if we set up the problem this way, then if we think about what's going on at the beginning of the problem, none of the chain has been wound up. So x would be starting at 0. And as we wind up the full chain, we would end up with x equal 50 to finish the problem. So letting x equal the length of chain that's already wound up makes sense because then x will be increasing. The idea is that in a minute, we're going to say that work is a certain integral between 2 x values of a certain function f of x with respect to x. And you want your x values to be increasing, meaning you want x to be starting at a small number and finishing at a big number, just because that's the way that we label the x values on an integral. We put the small one on the bottom, big one on the top. Now, if you had set up x differently, for example, if you let x equal the amount of chain still to be wound up, then x would be decreasing, and you'd actually have a sign error when you do the work. You would find negative work, which wouldn't make sense from a physical point of view. So it's always important in these types of problems, when you're defining x, to let x represent a variable that is getting bigger over the course of the problem. So while we're on the topic of the x values, let's think about what x values will specifically apply in the problem. Remember that we're not winding up the entire chain. We're just winding up 30 meters, meaning the first 30 meters of the chain. So in fact, the x values that we'll be using when we compute work, we'll be using x from 0 to 30. Okay, now let's think about our force, f of x. If we freeze the problem at any particular x value, what force is being exerted? Well, that's coming from the weight of the chain. And we know that the chain weighs 2 newtons per meter. I'm going to write down our units here. So 2 newtons per meter times, if we multiplied this by the number of meters of chain that we still got to wind up, then we'll have something in newtons. So we need to multiply that 2 by 50 minus x. And this is telling us how much the unwound chain weighs. So if we just simplify that a little bit, our f of x is 100 minus 2x. Units there are newtons, and this is the force that's going to be integrated to get our work. Okay, so now we can write down our general formula for work. Work is going to be the integral between 2 specific x values of your force function integrating with respect to x. We said that the x values in this problem are ranging from 0 to 30. So that represents starting when the chain is not wound up at all, finishing when you've got 30 meters wound up. What we're integrating, this force function, 100 minus 2x, integrate that with respect to x. And this will give us the total work done over the course of the problem. So during our integration, we get 100x minus x squared and that's going to get evaluated at 30 and then at 0. So just plugging in, we'd have 100 times 30 minus 30 squared, and then subtracting off the value at 0 would give us 0. So that comes out to 2100 Newton meters, or you could say 2100 joules, for the amount of work done in winding up that chain. Here's our second of 3 work examples. We're told that the gravitational attraction between 2 objects is F equal k over x squared, where x is the distance between the objects. K here would just represent a constant, an unknown constant. Find the work done in moving the objects from 20 meters apart to 40 meters apart. Well, since we have this unknown constant k in the problem, our answer will involve the unknown k. And let's think about how to set everything up. So just like in the last problem, we would first want to figure out what x is. That was actually given in the question, the distance between the objects. And let's think about what x values we'd be running through during the problem. So we want to find the work done in moving the objects from 20 meters apart to 40 meters apart. Okay, so at the start, x is equal to 20. At the end, x is equal to 40. And that makes sense. As we said in our first problem, you want the x values to be getting bigger or increasing over the course of the problem. And that's just so that your amount of work comes out positive, as it should. Okay, and then we need a formula for force. Well, in this problem, we don't have to think about it too much because it was given to us in the question. So when we're talking gravitational attraction, it's some constant divided by the square of the distance between the 2 objects. And then we're good to go. We can say work is going to be the integral from a to b, where a and b are just the specific x values. What we're integrating is our force function. So you can write f, or f of x, times dx. So let's plug everything in and we'll have our work. So integrating from 20 to 40, what we're integrating, k over x squared. So if you like, you might want to rewrite that as k x to the negative 2, just to make the integration go a little more smoothly, times dx. And then let's integrate. So we're going to bump up the power, becomes x to the negative 1, divide by that new power. So our integrand becomes negative kx to the negative 1, and then we evaluate at 40 and then at 20. So we could say this is minus k over 40, and then when we subtract off the value at 20, we're going to have a double negative, so it's going to be plus k over 20. Now, if you prefer, you might want to put this into decimal form. So 1 over 40 is 0.025. So we've got negative 0.025k, and then we've got plus 0.05k. And that way we can just give a decimal answer. 0.025k would be our answer. Units, the usual Newton meters, or you could say joules for work, and that k is an unknown constant. Third and final work example, we have a spring of natural length 1 meter that requires a force of 8 newtons to stretch it to 3 meters. Find the work done in stretching the spring to 3.5 meters. Well, first let's think back to Hooke's law, which governs springs. The formula is F equal kx, where F is your force, K is your spring constant, so that's measured in newtons per meter. Just depends on the specific spring that you're working with. And X is the amount of stretch. So let's think about our X values first. Based on what we just said about Hooke's law here, X is going to be the amount of stretch on the spring in meters. And let's see what our X values are going to be as we go through the problem. So we're told the natural length of the spring, and we're told what force is required to stretch it a certain amount. Okay, so this information here is just going to help us figure out K, our spring constant. But what we're ultimately trying to find in the problem is the work that's done in stretching the spring to 3.5 meters long. Okay, so that means initially the spring is not stretched at all. So X is starting at 0. And by the end of the problem, the spring is now 3.5 meters long. Okay, well, that's not 3.5 meters of stretch. That's 2.5 meters of stretch because our spring was 1 meter long. So it might be good to just look at each of these lengths here and write down how much stretch that corresponds to. So that's 2.5 meters of stretch. And when we say the spring is stretched to 3 meters, that's 2 meters of stretch. Okay, so the amount of stretch that this spring will be experiencing by the end of the problem is going to be 2.5 meters. So X will be running from 0 to 2.5, measuring everything in meters over the course of the problem. Okay, so now that we've got that figured out, let's go over here and look at Hooke's law, and we'll figure out what our force is. So what we're going to use now is this information that a force of 8 newtons stretches the spring to 3 meters. This is going to help us find our spring constant. Okay, so let's plug in. 8 newtons is equal to our unknown spring constant times the amount of stretch. Well, that corresponds to a length of 3 meters, which we said is 2 meters of stretch. So if we solve for K comes out to 4, and the units there, newtons per meter. So that describes the strength of our particular spring. Okay, so then if we want to think about the function, the force function that we're dealing with over the course of the problem, it's F equal Kx according to Hooke's law, and for this particular spring, K is 4. So for this particular problem, the F that we want to deal with is F equal 4x. So I'm going to put these two parts of reasoning here in different boxes so that you can see our logical progress here. So we first decided that X would represent the amount of stretch on the spring, and then second, we found a formula for our force function. So once you've got those two things, then you're ready to set up your integral. So here we go. We're going to say work is the integral between the two appropriate X values of your force function integrated with respect to X. So let's go ahead and plug everything in. We are integrating between X values 0 and 2.5. Our force function we decided here was 4x, and that gets integrated with respect to X. So let's go ahead and complete our integration then. Integrating 4x is going to give us 2x squared, and we're going to evaluate at 2.5 and then at 0. So we're just going 2 times 2.5 squared minus 0, and that's going to give us an amount of work in Newton meters. So that comes out to 12.5 Newton meters for the amount of work done over the course of the problem. So we've now done 3 examples of using integrals to calculate work. And to finish off this video, we're going to look at 3 other applications of what you can do with integrals. Next idea we're going to look at is the idea of the average value of a function. So suppose that you've got a function, might look like that. It's just some curve that goes over a certain stretch of the x-axis. Let's say it's running between x equal a and x equal b. What we want to do here is calculate the average y value along all the points on the curve. So imagine looking at all these different points on the curve. If you wanted to get an approximation of this, you could just look at, say, 10 or 20 points on the curve, just add up their y values and then divide by the number of points that you used. So that would give you an approximation to the average y value. In our picture, let's put a vertical axis on here. Let's say our average y value might look something like that. Okay, so let's see how the formula works, and then we'll think about that on an intuitive level and see whether that makes sense. So the average value, we'll call it y_av, and the way you're going to get it is you're going to integrate your function y between the appropriate x values, and then you're just going to divide by the length of that interval. So I think one good way to think about this formula is just in terms of units analysis. If we look at the numerator here, we're integrating a function y with respect to x. If x and y were measured in meters, this would give us meters squared, and then we divide by a certain number of meters. So sure enough, our units would be meters. And that makes sense that that would be speaking to the average y value. Another way to think about it is more geometrically. So when you look at the numerator here, when you calculate the integral of y, what you're doing is you're finding the area under the curve. So the numerator is giving you this area under your curve between those two specific x values, x equal a and b. And so this is giving us an area in meters squared. And if we then divide that area by the length of the interval, which is what we've got on the bottom here, then what you'd have left is the average y value over the course of that interval. So that's a little bit of insight into how the formula works. You can either think of it geometrically or in terms of units analysis. So let's try a problem where we actually use this formula. So let's find the average value of the function y equal x to the fourth from x equals 0 to x equal 2. Well, I might write down the formula here. So the average value, which we're going to call y_av, is going to be the integral of our function y times dx over the appropriate interval, and then that's divided by the length of that interval, divided by b minus a. Okay, so let's see if we can plug into this. We're going to be doing the integral from 0 to 2. What are we integrating? Well, it's just whatever our function is. So in this case, it's x to the fourth. Gets integrated with respect to x. And then let's not forget about the denominator here. We need to divide by the length of that interval. So you could write all over 2, but a more natural way to do that would just be to put a half right in front of the integral, like that. So you're taking 1/2 of the integral. Okay, that looks relatively friendly. Let's try it. So 1/2 times integrating x to the fourth, you have x to the fifth over 5. We're going to evaluate at 2 and then at 0. So 1/2 times 32 over 5 minus 0 gives us our final answer of 16 over 5. So let's sketch this just to visualize this. So let's say this is x equal 1 and x equal 2. And we have to be able to go up to y equals 16. So let's try to do this roughly to scale to get a good sense of what's going on here. So let's say that's y equals 16 there, and we're doing increments of 2 on the y-axis. Okay, so if we plot our function, which is y equal x to the fourth, passes through 0, 0, passes through 1, 1, passes through 2, 16. What the function is going to do is grow quite slowly in this part of the interval, and then it's going to experience pretty rapid growth after that. So when we ask what's the average y value over this interval, notice that it's just a bit bigger than 3. 16 over 5 is 3.2. So the average y value is right about here. So notice that our average y value is not halfway up. That's because the function is growing pretty slowly in the first part of this interval. And then it experiences more rapid growth after that. So that's a bit of insight into calculating average y values. Next formula we're going to look at is arc length. So what arc length represents is the length of a curve. So imagine that someone gives you a curve that looks like this. You can imagine that this curve is a piece of string, and you can imagine just pulling that piece of string straight and measuring it against a ruler. We're asking how long is that curve? That's arc length. So the symbol that we usually use for arc length is little s, and here's the formula for it. We're going to integrate from a to b, and what we're going to integrate, square root of 1 plus the square of dy by dx, integrated with respect to x. So let's just understand from a geometry point of view why integrating the square root might give us arc length. If we just look at our integrand, the thing that we're integrating, it's the square root of 1 plus, I'm going to expand that square and call that dy squared over dx squared. And on the outside of the root, we've got this dx, which we might rewrite as the square root of dx squared. And the reason why you might do that is because then you can multiply the roots together. Remember, when you have root a times root b, that's always going to give you root ab. So you can just create one root and multiply all that stuff together. Let's see what that would give us. So we'd now have a big square root. Multiplying the dx squared through, we'd have dx squared plus dy squared. Okay, so let's think about what that represents geometrically. So imagine that you've got a curve and you look at 2 points that are relatively close to one another on that curve. So the amount of change in x between those 2 points, you could call that dx. The amount of change in y, you could call dy. So then if you think about what is that hypotenuse, it's actually this number here that we just calculated. It's the square root of dx squared plus dy squared, according to the Pythagorean theorem. So what the integral is doing is it's taking your curve and it's moving just chunk by chunk along the curve, and it's saying, well, what's the hypotenuse if I drew a little triangle there? What's the hypotenuse if I drew a little triangle there? And it's just summing up these hypotenuse values. But in fact, what the integral is doing is it's doing an infinite sum. We're taking infinitely many of these little chunks, and they are infinitely tiny. So because they're infinitely tiny, our integral actually gives us the exact value as opposed to an approximation. So here's our example. We're given the path of a plane described in terms of a curve. We're told that this formula applies for x values at least 1. So you could just imagine drawing a rough picture. Let's say x equal 1 is here. Plugging in x equal 1, that gives you a y value of 0. And so our curve is doing something like this, just roughly, without doing too detailed of a sketch. What we want to do is find the length of the path for the x values between 1 and 3. So we actually want to figure out what is the length of this arc here. So I'm going to write down the formula for arc length. It is the integral from a to b of the square root of 1 plus the square of dy by dx. And that's getting integrated with respect to x. One thing we could do is just figure out what our x values are going to be. They're going to be running from 1 to 3. And the other thing we could do is we could take the derivative of y so that we're able to sub in here. So let's calculate dy by dx, looking at our function y up here. So the 3/2 is going to come down in front and multiply with the 2/3. The power on the brackets there is going to decrease by 1, so it's now going to become 1/2. We're going to keep the inside function the same, and then we're going to multiply by the derivative of the inside function, so 2x. Okay, so that's a little refresher on the chain rule. It's been a while since we've thought about that. So all our constants out in front here are just going to cancel right out nicely, and we've got the square root of x squared minus 1 times 2x. Now, for the arc length formula, it's not actually dy by dx that we want, it's actually the square of that. So we might as well square this thing so that we're ready to plug into our integral. So square of that, we're just going to square each of the factors. So the root x squared minus 1 becomes a full x squared minus 1, and the 2x squared becomes 4x squared. And then we might as well just multiply that out to make that a little easier to deal with. So that would be 4x to the 4th minus 4x squared. And now that we've got that, we're ready to calculate our arc length. So I'm going to write down the arc length formula again. We're going to get ready to plug in. So we're integrating from a to b. What we're integrating, square root of 1 plus the square of dy by dx, integrated with respect to x. So the numbers that are going to go on the integral are just whatever x values we were given in the problem. Let's scroll back up for a second. We were told x was going to range from 1 to 3. And then what are we integrating? Well, it's going to be a square root of 1 plus this dy by dx all squared, which we already calculated up here. So just plugging in, you'd have 1 plus 4x to the 4th minus 4x squared. And I might just rewrite that a little bit more nicely. I just think it looks better if the 1 comes at the back, and that's getting integrated with respect to x. So there's a bit of a trick here. 4x to the 4th minus 4x squared plus 1 happens to be a perfect square. It happens to be 2x squared minus 1 all squared. What that means is that the square root of this thing is the square root of this thing. Remember, if you square root a square, what you're getting is the absolute value of the quantity under the square root. And then as long as you can convince yourself that for the x values that you're working with, this thing is non-negative, then you're safe to say 2x squared minus 1. So the reason we're able to do that is because x is ranging between 1 and 3 in this problem. And so if we just plug in some numbers like x equal 1 into this, it's positive. If we plug x equal 2 into that, it's positive. X equal 3, it's positive. So the absolute value of 2x squared minus 1, if we think of this entire thing, for the x values that we're interested in, it's equal to 2x squared minus 1. In general, I think it's good just to emphasize the algebra rule that the square root of a squared is equal to absolute value of a. And then you want to just do a little bit of analysis and figure out whether that's going to be a or negative a. Most of the time, it'll just come out to a. So with that whole discussion out of the way, we're ready to just come back to our integral here and say this is the integral from 1 to 3 of 2x squared minus 1 integrated with respect to x, and looks like we're in the home stretch. So 2/3 x cubed minus x, and we evaluate at 3 and then at 1. So subbing in 3, you'd have 15, and subtract off the value at 1, well, that would be 2/3 minus 1. So overall, 46/3 for the arc length. So really what we're trying to accomplish with these problems around average value and around arc length is just the fact that we're comfortable plugging into a formula. Because as you move through engineering, you'll see a lot of situations where someone just throws a formula at you and you want to be comfortable plugging in and then doing something like an integration from there. So very last formula we're going to look at, we're going to talk about the surface area of a solid of revolution. So this goes back to our discussion of solids of revolution. Remember that if you take a two-dimensional area, something like this, and you revolve it around an axis, we're specifically going to talk about revolving around the x-axis here, then what you get is a solid. In this case, you get a cylinder, solid cylinder. And we're interested in talking about the surface area. So imagine that this solid is something like a tin can full of soup, and you just want to figure out, okay, how much metal would be required to form the outside edge of that can. So we would not be talking about, we're not talking about the top or bottom of the can, we're just talking about the side of the can. How much metal in terms of meters squared would you use to form the area of the surface? So here's the formula, and we'll talk about it from a geometry point of view. We're going to use capital S to represent the surface area. Remember, we used little s for arc length. So capital S for surface area. Sometimes I'll actually write SA like that just to represent surface area. So how you calculate it is you take 2 pi times a certain integral, and what you're integrating is y times the square root of 1 plus the square of dy by dx times dx. Okay, so let's think about this integrand in a little bit more detail. So just look at the thing that you are integrating. You could move the 2 pi inside the integral and say we're integrating 2 pi times y times a certain square root. If we think of it this way, we should be able to figure out what these quantities represent. So 2 pi y is representing the circumference of a circle. And we know that this part here is representing a tiny chunk of arc length. So let's see if we can put this together into a drawing. So let's imagine that you had this scenario where you're just taking something simple like a rectangle, rotating it around the x-axis, and the solid that you would be creating, as we mentioned a minute ago, would be this can of soup. So it's full of soup, and it's got some tin or aluminum, let's say, on the outside. So what our integrand is doing is thinking about the circumference of a certain circle. So normally we say circumference of a circle is 2 pi r. In this case, we're saying 2 pi y because y is what's representing the radius of the circle. Okay, so right now we're in units of meters. Circumference of a circle would be measured in meters. But if we multiply that by a tiny little chunk of arc length, so something like that, then all of a sudden we've got an area. So we've got a tiny chunk of surface area, which is now measured in meters squared. And so the idea is that if you take your solid of revolution and you break it up by doing these little tiny chunks in the x direction, and in each case looking at a circle, circumference of the circle, times that little bit of arc length. If you start adding up things like that, then you will get the surface area. And even if you have a more interesting solid, like we have in the picture at the top here, so let's say we take a shape like this, so an area like this, and revolve it, you end up with a solid that then has this sort of a shape. Okay, so you're still taking these tiny little chunks along your curve like that, and in each case you're talking about the circumference of the circle times that little bit of arc length. So you're getting an area that looks like that. And you could build infinitely many tiny little areas like that along your curve. And what the integral is going to do is sum up those infinitely many, infinitely tiny little areas and overall give you your surface area. What we really want to focus on is just being able to apply the formula. So let's jump into our last example. So let's find the surface area of a cone with height h and radius r. The idea is that this cone is a solid of revolution. So if you imagine taking a certain triangle like this and then revolving it around the x-axis, then that's how you're going to produce this cone. And let's think about the dimensions. So we want the height to be h, meaning we want this to be h, because the height of the cone is usually measured in this direction. And the radius here would be r, because the radius is usually measured in that direction there. Okay, so that gives us a little insight into our cone. And let's write down the formula for surface area, just because that will guide us in terms of what calculations we have to do here. So surface area is going to be 2 pi times the integral from a to b of y times a certain square root integrated with respect to x. Under the square root, we have 1 plus the square of dy by dx. Okay, so let's think about what we would need to calculate. I would say really the things that we need to figure out here are what are the a and b values that we're going to want on here? What's our formula for y? And what's the derivative of y? I would say if we could get those 3 things, then we would be ready to plug into our surface area formula. So what x values are we going to be running through in this problem? Well, x values between 0 and h, because h is this distance here along the x-axis. Next thing we said we need is a formula for y. Okay, so let's look at the hypotenuse of this triangle here. That is a line, and we should be able to figure out the equation of that line. So I think I'll redraw a copy of our triangle over here just so that our diagram doesn't get too cluttered. So here's our x and y axis. And if we label on here, we know h is this distance horizontally and r is that distance vertically. Okay, so let's come up with an equation for this line here. We'd say y equals mx plus b. But what's our y-intercept? Well, it's 0. So b is 0. And what's our slope? Well, slope is rise over run. Rise is r, run is h. So our slope is r over h. So that equation of that line just looks like y equals r over h x. So we can write that down. And then the one other thing we said we needed is dy by dx. So if you take the derivative of y with respect to x, you just get this constant r over h. Good. I think that's all the details we needed to figure out. So now let's write down our surface area formula one more time, and we'll see if we're ready to plug in. So it's going to be 2 pi times the integral from a to b, y times a certain square root, and we integrate with respect to x. Under the square root, we have 1 plus dy by dx, all squared. So I would say, yes, we're good to go in terms of plugging in. So we'll keep our 2 pi out in front. Our integral from a to b, well, we said our x values are going to range from 0 to h. So those are the numbers going on the integral. Our y value here needs to be written in terms of x. So we said that y is equal to r over h x. Great. And then we've got this square root. So under the square root, we've got 1 plus the square of our derivative, and we said our derivative was r over h. So we'll just sub that in there. And then we got the dx at the back. Okay, so I will admit that this looks a little scary, but the idea is that almost everything in here is a constant. right? The r over h is a constant, so that's just going to come out in front. The square root, actually, everything under the root is just a constant, so that just comes out in front. So let's do that. 2 pi r over h times a certain square root. All of that stuff just comes out in front. And then what are we left with? Well, we've just got the integral from 0 to h of x dx. So once you realize that, then you say, oh, okay, this is not too bad. So you got 2 pi r over h times this square root. And let's focus on our integration. So if we integrate x, we get x squared over 2, and that's going to get evaluated at h and then at 0. I'm just going to calculate this right in this step here. So if we actually subbed into this, we'd have h squared over 2. So at this point, you've got the correct answer, and it's now just a matter of how much algebra do you want to do to clean this up. So some things you could do to clean up, you can cancel the factor of 2 from the front and the back there. That's going to look better. You can cancel a factor of h as well. So you've just got a single h now, which you could move to the front. So you could write this as pi rh times the square root. I think that would be a really common way that people would leave their answer. So I'd say, yep, that's good. There's one other thing you could do. I suspect a textbook would probably do this last step of simplification, so I'll point it out. Take this h here that you see out in front, and you can think of that as the square root of h squared. And the reason why you might want to do that is because then you could multiply through the root and actually clear the fractions. So if you look at what we've got under the root, you could say that's 1 plus r squared over h squared. And then you can imagine that as you multiply this h squared through, that's just going to nicely clear the fraction under that root. So if you did that, you'd call that pi r times the square root of h squared plus r squared. And yeah, that looks pretty nice. So also a correct answer. As I mentioned, the course pack would likely write their answer in this form. But if you said this, on an assignment or a test, that's perfectly acceptable. Similarly, if you went sort of the middle route and did a bit of simplifying, that's also fine. The real point of the problem is just to be comfortable. If someone kind of throws you a weird formula, just to be comfortable plugging into it and doing your integration. So we did 3 examples of calculating work. We also looked at a variety of other formulas like average y-value, arc length, and surface area. Thanks for watching.